let's start talking about rotations. A rotation, as we mentioned yesterday, it's a turn around a particular coordinate. All right. A good example is here, where you can see that we're rotating the figure. And now we get to a second limitation of online classes. So there's a whole lot of things I love about online classes. For example, if you take a regular class, you can't just turn around and review the lesson and see the lesson repeated right in front of your eyes. But if you don't get a online class lesson, you can watch the video again. Many advantages to online classes. You can take them as when you can really concentrate. There's lots of things to do. However, as far as hands-on things, it's very difficult to do hands-on things in a online class. So we talked before about constructions really not being something that lends itself to an online class. And the best way I know of to teach a rotation is to literally turn your paper 90 degrees, see where the triangle ends up. Turn your paper 180 degrees, see where the triangle ends up. Turn your paper 270, see where it ends up. Unfortunately, that's not possible. And even for some students, that's still difficult. They have a difficult time seeing it and perceiving it. So there's a second way to know rotations, and that way is to memorize the rules. And normally I don't like to memorize. But in this case, this is one case where even for students in a class that meets face-to-face, sometimes memorizing the rules are best. And if you're online, memorizing the rules are best. So I would suggest taking a photograph of this slide for your class album on your phone. I think that would be wise. Right, because you can use these rules to answer homework and quiz questions and so on. And now let's get started to do some rotations. So we're asked to rotate the point 4 AB, which is made up of A is 4, 1, B is 2, 5, 90 degrees counterclockwise. So there are the 2 points, and there's the line segment that connects them. Here are, to rotate it counterclockwise. That's why it says C clockwise. So the rule, I wrote it down so you would remember it, is XY becomes negative YX. Now, whenever we have a positive rotation, like a 90-degree rotation, it's always counterclockwise. It's kind of redundant for me to write 90 degrees counterclockwise. We assume counterclockwise, and then if I say a negative rotation, it would go clockwise. So we want to draw the image of this, and the way we're going to do that, again, because it's easiest in an online class, and it's also easiest for probably a little less than half of the class in a face-to-face class, is to just plug in the coordinates and see what happens. Now, the rule is that XY becomes negative YX. So 4, 1 becomes negative 1, right? The Y goes in the front, and the Y was 1, so it goes in the front, and it gets negated. So that's why it becomes negative 1. And the 4, the X guy, that goes at the end. So the 4 goes at the end. So that becomes negative 1, 4. Same thing with the 2, 5. The Y at the end gets negated, goes in the front. That's negative 5, and the X goes in the back, too. So 4, 1 becomes negative 1, 4, and 2, 5 becomes negative 5, 2. And there is your image. So the best way to do it for online class purposes, and for, like I said, a little less than half of the students in a face-to-face class, is to just remember the rule. Just plug in the coordinates, calculate the coordinates, and then go graph the figure. Now, if you somehow are doing this on like your phone or a Chromebook or an iPad, and you want to turn the figure 90 degrees counterclockwise, you'll see that where the blue one starts, after you turn it 90 degrees, it'll be where the red one is now. Okay, with a stop and start, let's see you try the next one from beginning to end. Go ahead. Okay, so the first thing we do is we draw AB. Then we calculate the new coordinates. Remember, XY becomes negative YX. So the X, which is negative 4, that goes to the end. And the Y, which was negative 1, it gets negated and goes in front, so it's positive 1. Negative 2, negative 3. The negative 2 goes to the end and stays there. The negative 3 gets negated and goes in the front, so that's 3, negative 2. So therefore, I'm now going to mark the points 1, -4, and 3, -2. There they are. If you look quickly, it does look like if you turned it counterclockwise 90 degrees, the blue would land on the red. And as I said, if you have a phone or if you have an iPad, Chromebook, anything like that, you can see it happening as well. All right, so rotations are the hardest ones to do on without paper and pen to do them on. So you can remember the rule and crank them out. But we can often find rotation problems in the form of multiple choice questions. So the first one says if letter P, capital P, is rotated 180 degrees, which is the resulting figure? Remember, you're going to go counterclockwise because it's a positive 180. Not that it really makes a difference with only 180. And what would it look like when you're done? Okay, assuming you did stop and start, you can always doodle this on paper, but question or answer D is what it would look like, turning it around. And if you want to do a handstand in front of your computer screen, if that won't turn, you can do that. Or you can look at several other options with the Chromebook and the phone and just turn that thing 180 degrees. Okay, accompanying diagram shows a right triangle. Let's rotate this guy 90 degrees counterclockwise, which again is kind of redundant because if it's a positive rotation, it goes counterclockwise. Which of the images will it be? Okay, so it works out that B would be the correct solution. So if you can picture it, you spin this paper, you turn the X up to where the Y is. So as it points up now, as you're turning it, it'll point to the left. This bottom section of the triangle, see how that points up now? But when I turn it to the left, it'll point to the left. And that's choice B. All right, so those are rotations. Now let's talk translations. Translations. A translation is a slide, and there's like a vertical and a horizontal component to it, which are depicted by these green lines. See, if I asked you to go from where you live in your neighborhood to the local deli or whatever, you can't just like climb over people's houses and cars and front lawns and backyards. You have to kind of go east, west, north, south, following the streets. And that's what translations do. There's a horizontal component to them and there is a vertical component to them. So if I want to translate AB, which is the blue segment, A is -5,2 and B is -1,4. If I want to translate that according to the rule T5 -3, that means move 5 places to the right, because it's positive, down 3. And of course, I went down 2. So 5 to the right, down 3. I only went down 2. So sorry about that. When you see my picture drawn, I should have went down 1 more spot in each case. You can express T5 -3. There's really 3 primary notations for it. One is when you put it inside these less than greater than symbols. Okay, 5 -3. Another one is you could say xy becomes x plus 5 because you're going to add 5 to the y and subtract 3. Add 5 to the x and subtract 3 from the y. So my resulting figure is here. And just so you know, as I mentioned before, they should each be down 1. Okay, so this should be down to 0, -1. This point on the left end and the point on the right end should be down to 4, +1. So I don't make that mistake again. I hope not. Anyway, so next up. This one's on you. Translate AB according to the rule 5 -4. T5 -4. There you go. Go ahead. You're up. All right. So where are we going to go here? What are we going to do? Well, we're going to go 5 units to the right, count them, and we're going to go down 4 units. So let's see, we go 1, 2, 3, 4, 5 to the right, 1, 2, 3, 4 down. That's starting with this top point. Now let's do the bottom point. 1, 2, 3, 4, 5, 1, 2, 3, 4. So in both cases, I went 5 to the right and down 4, and then I connect the dot. Okay. Now it's also possible to have done this a different way. Now remember, we do have other ways to express t, standing for translation, 5, -4. We could do it with the less than greater than signs, where you move 5 right, down 4. Or you could do xy becomes x plus 5y minus 4. But we could have calculated the points and then drawn the points rather than calculated them counted them on the graph. The way we do that is we just add 5 to the x and subtract 4, or add -4 to the y. So -3 plus 5 is 2. 2 minus 4 is -2. And there's the point right there, 2, -2. The higher point, -1 plus 5 is 4. 5 and -4 make 1. And there's the point, 4, 1. So you can also apply the rule to the coordinates and calculate the point, and then you'll get the solution, okay? So let's do some calculations here. The coordinates are on the left, and then the 3 different notations are across the top, 3 different translations. The first one, t -2, 7, means subtract 2 from the x, add 7 to the y, or if you were doing this, you'd go 2 left, because you're going negative, 2 left, up 7. The next one says you're going to add 3 to the x, subtract 8 from the y, or go 3 to the right and down 8. And the last one says xy becomes x plus 1, y minus 2. That means add 1 to the x, or go 1 to the right and then down 2. Okay, so I'll take you through the point 3, 5 with each of these, and then you'll do the next two. So if I plug in or apply the rule, translate -2, 7 to 3, 5, 3 plus -2 is 1, 5 plus 7 is 12. If I apply this rule, 3, -8, 3 plus 3 is 6, 5 and -8 make -3. If I apply the next rule, 3 plus 1 is 4, 5 minus 2 is 3. Okay, so you do all of -2, -1. Do all 3 answers to -2, -1. I will put them up on the board in just a moment. Go ahead. Okay, so first, in the first problem, I'm going to subtract 2 from the x, add 7 to the y. That gives me -4, 6. In the next one, I'm going to add 3 to the x, subtract 8 from the y. That gives me 1, -9. And in the next case, I'm going to add 1 to the x. And sometimes I say subtract 2, sometimes I say add -2. I'm actually more partial to looking at it as add -2. So -2 plus 1 would give me 1, and -1 minus 2 would give me -3. I'm sorry, -2 plus 1 is -1. Okay, you try the last row. Go ahead. All right, so -3 plus -2 is -5. 5 and 7 make 12. -3 and 3 make 0. 5 and -8 make -3. -3 and 1 make -2, and 5 and -2 make 3. So that's a good chart to have you learn how to calculate answers to translations. You always add and subtract to get answers to translations. Now, under a translation, xy becomes x plus 3y minus 1. Find the preimage of 5, 9. Now, this is a little tricky. This is saying the answer, in other words, the guy in red on the inside, is 5, 9. What must the rule at the top have been? Or, I'm sorry, and the rule at the top is given. What point did we have to start with? So you're kind of going backwards here. Go ahead. So you had to start with the point 2, 10. Right? 2 plus 3 would give you 5, and 10 minus 1 would give you 9. Now you can think of it as going backwards. If the rule says to add 3, and you have the output or the image, and you're trying to find the preimage, well, that means if I added 3 to get 5, I have to go 5 minus 3 to get back to what I started with, which is 2. So you're doing inverse operations here. Likewise, if you subtracted 1 to get 9, you have to add 1 to find what you started with, which would have been 10. Let's have you try it again. Go ahead. Okay, so the output, the final image is negative 2, 3. It wants you to find the pre-image. In other words, what you start with to get negative 2, 3. And it is 3, 1, right? Because if you plugged in a 3 minus 5, you would get negative 2. And if you plugged in a 1, 1 plus 2 would give you 3. Remember, work backwards. If this says you add 2 to find what you started with, take the 3 and subtract 2. If this says negative 2 at the end, and you have to subtract 5 to get there, add 5 to find out what you had to start with. All right, so that's translations. Now let's talk dilations. When it comes to dilations, and remember, it's not dilations, it's dilations. Dilate is the word that you're working off of here. The segment AB with coordinates A, 3, 1, and B, 2, 5 is dilated under the transformation D2. Now, a dilation is the only one that's not an isometry. Remember we talked about that word isometry yesterday? Isometry keeps the size the same. A dilation does not. As such, a dilation multiplies. Okay? So let's graph AB. There it is. So what we want to do now is you want to take the coordinates of AB, and it's a transformation, it's a dilation, so you're going to multiply by 2. Look at the D for dilation as being likewise in the word product. Okay? Go ahead, see what your image would be. So 3, 1 times 2 is 6, 2, and 2, 5 times 2 is 4, 10. 3, 1 times 2 is 6, 2, 2, 5 times 2 is 4, 10. And then I just plot those points, okay? So there's 6, 2, and up here is 4, 10. And look, it looks twice as big, so that makes sense. All right, now we don't graph dilations too often because the numbers can get really big. But we do a lot of questions like these. What are the coordinates of the point negative 1, 4 under a dilation of D negative 2? Go ahead. Okay, so you're going to multiply. Negative 1 times negative 2 is 2, and 4 times negative 2 is negative 8. Again, negative 1 times negative 2 is 2. 4 times negative 2 is negative 8. All a negative does is make it flip to the other side of the coordinate plane, okay? Next, if the dilation D sub k, negative 2, 4 equals 1, negative 2, the scale factor k. The scale factor is always what we called down here. So on the previous problem, the scale factor was negative 2. So we want to know what's the scale factor here. If we go from negative 2, 4 to 1, negative 2, what's the scale factor? It's a half, right? Negative a half, actually. The correct answer is negative a half. I think I put down negative 2, but it should be negative 1/2. All right, because you're dividing by 2. So negative 1/2 is the correct answer. Which of these transformations represents a dilation? Well, let's look at the first one. In the first one, you're adding 3 and then adding 3. Adding is a translation. The next one, you're negating the x part, but the y is staying the same. And we're looking for multiplying. That clearly doesn't multiply. The next one, we're flip-flopping places, we're not multiplying. The next one, though, look, 8 to 4, 4 to 2. Each of them are being halved, so that's a dilation of 1/2. Okay, let's find the image points of each of these. Go ahead. Do them one at a time. Okay, first one. 3, 5 under the dilation of 4, so we're going to multiply by 4, and I get 12, 20, right? 3 times 4 is 12, 5 times 4 is 20. Okay, try the next one. Yep, we're going to get negative 3, 9, right? Because negative 1 times 3 is negative 3, and 3 times 3 is 9. What about the next one? This is a dilation of 0.5, which is like half or dividing by 2. Okay, we're going to get negative 1, 3, right? Because half of negative 2 is negative 1. Half of 6 is 3. What about the last one? Negative 3 times negative 3 is 9, and negative 4 times negative 3 is 12. The image of point A after a dilation of 3 is 615. What was the original location of point A? Remember about inverse operations. 615 is the output. We want to know what the input was. What did you start with when you did a dilation of 3 to get the 615? 2.5, right? 2.5 times 3. 2 times 3 is 6. 5 times 3 is 15. All right, we got 2 more questions for you to do. Try them both and I'll give you the answers to them. Go ahead. Okay, the point 6.3 maps onto a prime 2.1, and it's under a dilation with respect to the origin, which is all we're doing. What's the constant of dilation? Well, did you notice how we're dividing by 3, right? 6 divided by 3 is 2, 3 divided by 3 is 1. So that's a dilation of 1/3. For some reason, my equation editor does not let me do subscripts of, well, actually maybe I could do it, but I don't know right away how it works, so I just wrote 1/3 that way. Next, under a dilation with respect to the origin, the image of negative 15.6 is negative 5.2. What is the scale? Again, you're dividing by 3 in both of them, so it is 1/3. Okay, we've done all of our work with transformations and coordinates. You can exhale now. Of course, you have a homework to do and a quiz to take, but next week is going to be a test week.